What happens when you mix two of the most powerful forces known to humanity and nature? Imagine taking the destructive heart of a star and plunging it deep into the belly of a slumbering earthly titan. This isn't a scene from a blockbuster movie, it's a question that tickles the imagination. A question that pits our greatest weapon against our planet's greatest geological threat. What if we dropped a nuclear bomb into a supervolcano? Would it trigger an apocalypse? A world-ending eruption of ash and fire, blotting out the sun and plunging our civilization into a new dark age? Or would it be something else entirely, a cosmic fizzle instead of a planetary bang? Let's embark on a journey to find out. What is a nuclear bomb? At its heart, it is a device that unlocks the fundamental energy of the universe. Einstein. E equals mc squared. Energy equals mass times the speed of light squared. This simple, elegant formula tells us that a tiny amount of matter can be converted into a tremendous amount of energy. The speed of light is a huge number, and when you square it, it becomes astronomically large. This is the secret of the atom's power. The first is called fission. This is what happened in the first atomic bombs. You take a heavy, unstable element like uranium or plutonium. This creates a chain reaction, a cascade of splitting atoms that grows exponentially in a fraction of a second, culminating in a massive explosion. The other method is fusion. This is the same process that powers our sun and all the stars in the cosmos. Instead of splitting heavy atoms apart, you smash light atoms together. You take isotopes of hydrogen, the lightest element, and under immense heat and pressure, you force them to fuse into a heavier element, like helium. When they fuse, a tiny fraction of their mass is converted into a colossal amount of energy. That's why hydrogen bombs or thermonuclear weapons are so much more powerful, a tool that brings the destructive power of the stars down to Earth. Now, let's journey deep into our own planet. Our spaceship Earth is not a cold, dead rock. It is a dynamic living world. Deep beneath the surface is immense heat and pressure. Heat left over from Earth's formation and radioactive decay melts rock into magma. Magma can find its way up through the crust. We call that a volcano, but some volcanoes are different, far, far larger. We call them supervolcanoes, the sleeping giants of our world. A supervolcano isn't defined by the mountain on top. Many don't look like volcanoes. Calderas can be dozens of kilometers across. The real action is miles below the surface. A gargantuan magma reservoir slowly grows there. Not a small lava pool. A molten body the size of a major city. Yellowstone's magma chamber is about 90 kilometers by 30 kilometers. It could fill the Grand Canyon many times over. So we have our two contenders. In one corner, the nuclear bomb, the pinnacle of human destructive technology. In the other, the supervolcano, a geological force of unimaginable scale. To understand what might happen when they meet, we need to compare their power. Scientists often measure large explosions in terms of tons of TNT. A 1 megaton nuclear bomb, a fairly standard size in the arsenals of major powers, has the explosive energy of 1 million tons of TNT. The largest bomb ever detonated, the Tsar Bomba, had a yield of over 50 megatons, 50 million tons of TNT. Now let's look at the supervolcano. From that, they estimate the total energy released, about 240,000 megatons of TNT. Think about that, not 240,000. That's more than 4,000 times the energy of the most powerful nuclear bomb ever built. If you were to detonate the Tsar Bomba every single day for over 11 years, you would still not equal the energy released by the last Yellowstone super eruption. Comparing a nuclear bomb to a supervolcano is like comparing a firecracker to a hurricane. One is a loud, impressive bang. The other is a vast, self-sustaining weather system that can reshape coastlines. The scale is simply in a different cosmic league. So let's run the thought experiment. We take our 1 megaton nuclear bomb. We drill a hole miles deep into the Earth's crust, right into the roof of the magma chamber beneath Yellowstone. We lower the bomb down, and we detonate it. What happens in that instant? The bomb explodes. For a microsecond, a sphere of plasma hotter than the sun's core appears deep underground. It vaporizes the bomb itself. It vaporizes a significant amount of surrounding rock. An immense bubble of superheated gas, with pressures millions of times greater than the atmosphere, is created. This bubble expands violently, generating a powerful shockwave. This shockwave would be incredibly destructive, but only on a local scale. It would shatter and pulverize the rock immediately surrounding the detonation point. Think of it like a massive underground hammer blow. It would certainly create a powerful earthquake, one that would be felt for hundreds of miles around. The ground would shake violently. It might cause landslides, damage buildings on the surface. Now here's the critical question. Is this shockwave, this underground blast, enough to uncork the magma chamber? Is it enough to rupture the roof of the chamber, which can be 8 to 10 kilometers thick? The answer, according to the scientists who study this, is almost certainly no. The pressure from the bomb, while immense at its source, dissipates rapidly as it travels through the rock. It's like shouting in a huge, crowded room. The people right next to you will hear you clearly. But by the time the sound reaches the back of the room, it's just a faint murmur. The bomb's energy is just not enough to blast its way through miles of solid and semi-solid rock. Think of the magma chamber as a giant, incredibly tough balloon and the bomb as a pin. But this balloon is wrapped in miles of granite and other resilient rock. Poking it with a pin, even a very powerful nuclear pin, isn't going to pop it. It would be a spectacular underground firework, but it wouldn't have the sustained force needed to peel back the lid on a system that is continental in scale. The bomb is a sprinter, the volcano is a marathon runner. The bomb's burst of energy is simply too brief and too focused to affect the entire system. Let's assume for a moment that the bomb's blast does manage to crack the rock and connect with the magma chamber itself. What then? Does the magma suddenly explode? This is a common misconception. The magma in a supervolcano's chamber is not like a tank of gasoline just waiting for a spark. It's more like a very thick, very hot, very gassy tub of honey, or like taffy. Its potential to erupt comes from the immense pressure of the dissolved gases trapped within it. For a super eruption to begin, you need a massive, rapid depressurization of a significant portion of the chamber. The detonation of a nuclear bomb would introduce a huge amount of heat and a shock wave into a tiny part of this vast magma reservoir. The heat would locally superheat the magma. The shock wave might cause some of the dissolved gases in that immediate area to come out of solution, like bubbles forming when you open a soda can, or like an Alka-Seltzer tablet fizzing in a pool. This might create a localized burp or a small phreatic steam-driven explosion as groundwater flashes to steam. That could be dangerous on the surface, maybe a new geyser or hydrothermal explosion. But, honestly, it's a far cry from a full-blown super eruption. The problem is really one of scale. The magma chamber beneath Yellowstone holds somewhere between 10,000 and 45,000 cubic kilometers of molten and semi-molten rock. A nuclear bomb might disturb a few cubic meters or maybe a cubic kilometer at the most generous, optimistic estimate. Let's focus on Yellowstone. It's the supervolcano that captures the public imagination the most. The United States Geological Survey, the USGS, is responsible for monitoring Yellowstone. They have addressed this question directly. Their scientists ran the numbers and considered the physics. Their conclusion is unequivocal. We do not possess the technology or firepower to intentionally trigger the Yellowstone caldera. That idea belongs in science fiction. The USGS points to natural forces at work. An eruption requires a massive change in magma chamber pressure. A huge new batch of magma surges up from the mantle, raising internal pressure. Or the crust above the chamber is significantly weakened. A nuclear bomb does neither on the required scale. Its energy is a tiny pinprick next to geological forces. Much of Yellowstone's magma isn't a free-flowing liquid, it's a crystalline mush. Solid crystals and liquid melt together maybe only 5 to 15% molten. That makes it viscous and resistant to movement. The shocking truth, our greatest weapon is no match for the geologic stubbornness of a supervolcano. When we look across the scientific community, from volcanologists to geophysicists, a clear consensus emerges. The idea of nuking a volcano to trigger an eruption is a non-starter. The energy mismatch is the primary reason. The complex plumbing system of a volcano is not a simple pipe to the surface. A bomb might disrupt a small part of this network, but the system is vast and redundant. This topic was even explored in a 2017 study by NASA scientists. They weren't looking to trigger an eruption but to prevent one. Their idea? Drill into the side of the Yellowstone magma chamber, pump water down to cool it. Even in this controlled scenario, they highlighted extreme danger. What a bomb would do is create a radioactive mess. So, what have we learned on our journey? We've seen that a nuclear bomb harnesses the power of the atom, unleashing stellar energy on a human scale. We've journeyed into the Earth and witnessed the sheer scale of a supervolcano, a geological engine of immense power that has been building for eons. When we place them side by side, we see the profound difference in their nature. The bomb is a momentary flash of brilliance. The volcano is the slow, inexorable breathing of a planet. A single shout in a hurricane, a firefly in the glare of the sun. The bomb simply lacks the power to command the volcano. This thought experiment is more than just a fun what-if scenario. It teaches us about perspective. It's a humbling lesson in cosmic and planetary scales. We humans, with all our cleverness and technology, can feel like masters of our world. We split the atom, travel to the moon, communicate across the globe in an instant. But we are still subject to the grand, sweeping forces of the universe and our own planet. It's a reminder of our true place in the cosmos. Does this mean we have nothing to fear from supervolcanoes? Of course not. A super eruption would be a global catastrophe, and that's why scientists monitor them so closely. But the threat comes from nature, from the internal clock of the planet itself, not from a villain in a secret lair with a nuclear missile. The Earth is more robust, more resilient, and more powerful than we might imagine. It is not a fragile bubble waiting to be popped by our folly. And in a universe full of terrifying possibilities, there is a strange comfort in knowing that some giants are simply too big for us to wake.